So I think we've already covered this. My name's Katie and I'm talking about design. So to set the scene, we have data from an array of sensors, and we know that they provide us with this holistic understanding of water quality dynamics like we've seen. And monitoring efforts, effectively monitoring is affected by the location of sensors. And by location, I mean in both space and time. So optimal design offers a framework to address this problem of sensor placement such that information retrieval is maximized depending on some given cost and utility. So what is optimal design? Generally speaking, it can be compartmentalized into 4 different components. So we have some sort of a model. We have some response variable y, some covariates x, and some understanding of how they interact. So it could be like water temperature as y variable and something like air temperature as x. And I'm going to use parameters to describe how these interact within the assumption of a model. We have data. We may or may not have data, but we have a principled way to incorporate that. We have a utility function. So this quantitatively defines the objectives. So it could be to minimize variance into the predicted values. It could be to minimize variance in your parameter estimates or to better estimate trends. And it could be related to the quality of data, which would mean something like you've more accurately detected anomalies and taken them out, so you're left with a better data set. So that's his utility and how it's quantified. But then we need to search over all the possibilities of design points. So that's some design space, capital D. So we search over that in an effort to maximize the expected utility. So we've spoken about this quite a bit. I'll keep this brief because it's one of 2 main challenges in this project regarding the design. So the first is that we have data from sensors, these in situ water quality sensors. So this is a photo of the BlueScope sensor. It's about this big. We threw it into the water. Edgar had a photo of him, a video of him throwing it in. I couldn't let him be the only one with that. So happy faces as we went on that field trip to the Hobart River. So we have this data, and as we've seen already, it's inherently non-stationary and it's challenging with these types of data, types of anomalies to accurately detect them. And these are, again, with the same types of anomalies we've seen throughout the day. So one of the questions I'll be addressing in my PhD is, what if the instances of anomalies are the same, so the 0, 1 labels, but the types are renamed? So there's slightly nuanced kind of, so instead of what it looks like, so sudden spikes, sudden shifts, it's more like the reason for the anomaly. So the battery failure or biofouling of the probe, whatnot. So it's a different use case, and there's a variety of methods, which I'll talk a bit more about later, but I'm particularly interested in machine learning applications with this new data set, essentially. So. Second challenge with this application of optimal design is the river network characteristics. So the branching network topology and the directionality and volume of flow. So as Edgar's already mentioned, we have some points on a river network, S and T, and they meet at some confluence, U, and their relationships are characterized by this hydrological distance between them as opposed to the Euclidean distance. And I'm mentioning this just once more so it's front of mind, because the design kind of builds on this assumption of the modeling assumption. So in terms of the correlation models that we use, we see this decay over distance. So for example, it could be the hydrological distance over space or over time. But just consider this exponential model, for instance, and we see that depicted on the left. And they're kind of stretched and pulled by these unknown parameters, which we figure out when we fit the model to some data. So consider, consider this linear decay. Essentially, it's unknown. So at this point, I just wanted to highlight the fact that we might get more information out of sites depending on where they're placed because of the distance between them. So if you can imagine all of the sites are separated by a distance greater than this range, or alpha, then you won't get any information about the relationship, the spatial correlation, right? And this relationship on the network topology traces out a kind of a family of autocorrelations, not just the one case of the linear decay, but as these points vary across the branching network, we're left with something on the right. So I'll move on. The aims and objectives of my PhD project. So I'm 1 year in to the project and there's 2 years ahead of me. So I'll be speaking about kind of where to go from here for about half of the time. So the overall aim of this research is to develop a robust Bayesian design framework to handle these complex covariant structures in the stream network model given anomalous data. So you might be thinking, what is Bayesian and why are we interested in it? Essentially, the Bayesian framework offers us this principled way to capture this uncertainty, particularly in these parameter spaces, and propagate that through to the sampling implications. But also, as a byproduct, it allows us to incorporate, for instance, third-party data into the modeling and then into the design. So the roadmap to get there is through these list of objectives. So develop a Bayesian design method for stream network models. Currently, this doesn't exist in the literature, but we've developed, it's an order of magnitude more computation compared to the current design methods in this space, but we've compensated by using kind of rapid approximation methods in the utility. So that was step number 1, just get the framework in a Bayesian context for these models. 2, as I was mentioning before, we're interested in machine learning algorithms to identify these anomalies with this kind of nuanced label set. And we can use some combination of what already exists in the literature. And number 3, so basically we have some sort of method to detect anomalies, and now we want to incorporate that back into the design. So that's number 3. And then number 4, we've made this overarching assumption in the design assumes kind of one model to be true, but it might not necessarily be the case. So to make it more robust against the choice of model is the final point. So there's also been some work, which I won't get into now, about the kind of search algorithm. So what we looked at was a temperature data set from collected in the Clearwater River Basin in the USA. So this is from the Northwest Stream Temperature data set, or Northwest for short. Sorry, I'll just go back. And so the design problem was to choose the best 5 locations from 18. And where we have the slope, elevation, watershed area, and air temperature as covariates. And like Edgar touched on before, we're interested in the temperature of water because the fish populations that are sensitive to the temperature in the USA. So what we looked at We found the optimal design based on the subset, based on the 18 sites that were there. But then there was a problem. There's a problem with addressing the need for accessibility constraints. So whenever we deploy a sensor, there's almost this unknown about how accessible it's going to be. So if we consider a design problem where we want to deploy 2 sensors in some area called neighborhood N2, neighborhood 2 here, and another sensor around this area, conditional on all the other sensors. So if we kind of calculate a utility surface across this space, it looks like what's on the right. So flat areas are high utility and low utility, darker shaded areas. And really what this is telling us is that of the kind of neighborhoods that are selected, it doesn't really matter in neighborhood 2 where you put the sensor. It's kind of agnostic to where that is. But in neighborhood 1, there's a particular area of interest that's the best place to put it. And you'd probably want to avoid 3, 9 here. So you probably want to put it around this area and avoid that area, which we can tell from this kind of heat map here, which is discretized. But we could go a step further and fit a Gaussian process and have that kind of as a smoothened surface representing if I'm interested in this area, and if I walk upstream or downstream, then I know how effective, conditional on all the other sites, that putting a sensor in that particular location will be. And imagining a smooth surface, you can kind of have some contours of design efficiency, right? So we know what the best utility is in this area here, and dividing everything by that, we have some sort of, we can say things like walking 50 meters downstream will land us in a 90% efficiency, a design efficiency, whereas walking upstream 50 meters, we're out of that good utility zone. So that's been some interesting results so far and what we've looked at. We're writing up a paper at the moment with these and other results inside, and that'll be on archive in a few months. So keep an eye out, I'm sure I'll send it around. So just to finish up, just wanted to say that optimal design offers this framework to address the problem of sensor placement, depending on some given cost and utility. And I'm looking at developing a robust Bayesian design framework to handle the nuances of the stream network modeling. And we've demonstrated that we can have flexible outputs in design as well based on needs of partners. So demonstrated that we can have some sort of heat map around inaccessibility, so we can compute this beforehand, go out and kind of make decisions on the spot as opposed to rerunning quite a lengthy algorithm. So thank you.